Hello student, welcome back. Let's go to section 2. Section 2 is a review from previous lesson, section 5 of lesson 14, but there may be some students who just skip that and coming directly here. For those students, I'm going to cover it as normal speed, not in the review speed. For those students, this is not a review anymore. So let's assume that everybody is doing this for the first time. And let's do it in the normal speed. Okay, let's consider a non-homogeneous first-order linear system of ODEs with constant coefficient. Yes, this matrix has to be a constant coefficient matrix. Previously, we didn't have this part. Now we do. Also, previously we considered only when this was just y of 0. This time, let's make it a little bit more general. In that case, what do? Well, let's consider the homogeneous case first. So, partly as a digression, and partly as a review. Let's consider a homogeneous case first. So let's copy and paste this thing here, and let's consider this part. In that case, the solution formula will look like this. Y of t is e to the at power times y star, and that's when we had this. I hope everybody remembers that. But if I have t0 here, then we have to make appropriate shifting, so we'll have to do it this way. Let's check. Okay, let's take the derivative. Then by chain rule, exponentials stay the same, yes, but, excuse me, what did I do? I didn't copy paste completely. Exponentials stay the same, and then multiplication of this constant coefficient matrix or constant coefficient column vector will stay the same. But by chain rule, we have to multiply the derivative of the inside, and that's going to be a. You see, this minus t0 doesn't do anything because that's constant, so if you take the derivative, that becomes 0. The derivative of at, that's going to be a, and let's multiply by that. It doesn't matter whether I multiply here in the left or here in the right, because they're going to commute anyway. Alright, so what do we have? This is y, so this is equal to a times y. And what did I get? We did get the ODE. So yes, we got it. That part is done. How about the IC part? Okay, let's consider that. So here I'm plugging in t equal to t0. So okay, I'm putting t0 right here. And what did I get? t0 minus t0, that's 0, isn't it? E to the a times 0, so we have 0 matrix, times y star. And e to the 0 matrix, what is it? It's the identity matrix. Remember, e to the 0 power is 1, and the counterpart for matrix arithmetic is e to the 0 matrix power is identity. So we have what we want here. We want is the IC here, and indeed, we got it. So what does that tell me? This is the formula for the solution of the homogeneous part. If I drop it, and if you get this blue equation, the homogeneous equation, then this is the solution. In general, what do I want? Here we want solution of the homogeneous equation. we're going to get this kind of structure. And this one we actually found out here. So this one here is this, and then plus yp. Oops, what did I do? Okay, something's not right here. Okay, now it's correct. So the solution of the homogeneous part, which I just highlighted in blue, is this one. And the particular part, well, I have to work on it. And as for the blue part, the solution of the homogeneous equation, well, this blue equation is a homogeneous equation. And then this formula here is the solution of the homogeneous equation, which we recycled here. So far, so good. But bigger problem is how do we get yp? So let's work on it. Ready? Okay, let's get this yp, the particular solution. And the method we are going to employ is the same method that we used in lesson 2a, I think. Is it lesson 2a or lesson 2b? I'm not completely sure. We did it in week 2 in any case. In lesson 2a, I think, we did the method of integrating factor to solve a first order linear ODE, and this time it's not a system, just plain single linear ODE, just first order. And it was like this. If you have this kind of equation, then we get the integrating factor e to the antiderivative of this coefficient function. So we had this. And we multiplied this integrating factor to each term here, and then it turned out the left-hand side can be combined into a single derivative by applying the product rule backward. I hope everybody remembers. If you don't, maybe you can stop this playback and go back and review that lesson 2 and come back here. That's basically we are up to, except that this time we are doing all these in matrix systems. But there's something much simpler that's going for us. That is, this part here is just a constant matrix. Instead of P of t, which can be quite complicated, we have just a constant. So the antiderivative of this negative a is e to the negative at here. Just antiderivative is just negative at here. So take the exponential, then we have e to the negative at. And this is the integrating factor, which is analogous to this one for one-dimensional counterpart. This is what we did in lesson 2a, and this is what we are doing now, and please look at the parallel here. Okay, we have the integrating factor, and this is a justification, by the way. This part here is the antiderivative of just this coefficient part, negative a. All right, let's multiply this integrating factor to each term of this ODE here. There you go. There we multiplied, there we multiplied, and then there we multiplied. One little subtlety here. In lesson 2, it didn't really matter where I multiply this thing. To the left or to the right, it didn't matter, because in one dimension, multiplication is commutative. Here, in matrix arithmetic, the multiplication is not commutative anymore. Moreover, it's not even defined here. This matrix exponential is a square matrix, n by n matrix. This one here, this one is column vector, n by 1 column vector. So this multiplication is well defined, but if I switch the order, the multiplication is not well defined anymore. N by 1 times n by n, that's not defined. Same here, square matrix n by n, this is column vector n by 1. Square matrix n by n, and the column vector n by 1. So this multiplication is well defined, all good. Now let's make one more observation here. What about this a here? And then times a here or times a to the left doesn't matter because exponential and then this matrix A will commute. So whether I multiply to the left hand side or right hand side doesn't really matter. In any case, this is actually the derivative of this guy here. Derivative of this is this, and then derivative of that is this. So what do we have here? This whole thing is in the structure of the product rule. So we can combine the left hand side into a single derivative like this. Or if you want to check, start from here and then take the derivative using the product rule and the chain rule and see if you get the left hand side here. The only thing that you have to be a little concerned about is this multiplication by a, whether I can multiply here or to the left, but it's okay because the multiplication is commutative in this case. Both are about matrix A, again matrix A, so they are commutative, no problem there. So we have this. We successfully simplified the left-hand side into a single derivative. So we can take the antiderivative here. But be careful. If we have just one-dimensional function, then we can take the antiderivative freely, and then we are going to get the integral constant popping up. For matrices, don't do that. Antiderivative or indefinite integrals do not work very well. So please take the definite integral. Definite integral, t going from somewhere to somewhere. Where do we start? And the obvious starting point, of course, is the IC. So let's take the definite integral of both sides from here to there. The right hand side, no problem. Integral from t0 to t, okay, starting from t0 to arbitrary t. And then I already used up t, so I have to change some characters to something else. I choose u. So replace those t by u, and then going from t0 to t. Well, standard technique for the fundamental theorem of calculus and the definite integral. The left-hand side is a little bit more interesting here. We have the derivative and then definite integral. So the fundamental theorem of calculus applies. That this integral is basically the antiderivative, so it'll cancel each other out with this derivative computation. But you have to plug in the top and you have to plug in the bottom and subtract one from the other. So plug in the top, plug in t, we get this. Plug in the bottom, we have to plug in t0, and that's what this one is. As a matter of fact, I may have jumped ahead a little bit. If I plug in the bottom, we get this. Let's see, shall I increase the font a little bit further? Okay, t0, which I just highlighted in green, to t, which I just highlighted in blue. Okay, so t0 to t, and plug in t, we get this and that substitution in place of this u and that u. Now plug in t0, we get this and that substitution. Do you see those blue and green substitutions? They are coming from the definite integral of the derivative and the fundamental theorem of calculus. And then make final observation here. What is this y of t0? That's actually the initial condition here. So replace that with y star. And that's how that's how it was written originally. So it's all right. So we took care of the definite integral. It feels a little bit weird after it's getting suddenly small. Okay, from here, our job is to get y, so let's solve for y. Flip this one to the other side by adding it up to the other side, and that's going to give me the first line here. Remember, we're looking for y of t from this ODEs. From here, I have to solve for y of t. So flip this one to the other side and we have this. Okay? And then we have to divide this one away. So how do I divide away this? If this is a real number, it's easy, but this is a matrix. How do I divide by a matrix? By multiplying the inverse matrix. Does it exist? Well, yes, because this is exponential. The matrix A may or may not be invertible, but the exponential is always invertible, and the inverse of e to the negative at is, I have to take another negative, so e to the positive at. So that's the inverse, so multiply by the inverse. Finally, I got y of t taken care of. This is perfectly fine, but let's go to one more simplification. You see, we have e to the at, e to the negative at, so let's use the exponent rule and combine those together into single exponential. Can we do that? The answer is yes, because these two, a and negative a, commute. If they are not commutative, then you cannot use this exponent rule, but they are commutative, so yes, we can do that. Again, the same thing. A and negative a are commutative, so we can combine those into single exponent, and we can get that. And finally, we got this derivation. And that's the solution formula here. So here is the ODE, or the system of ODE. And then with some difficulty, using all those methods of integrating factor and so on and so forth, we ended up with this expression. The solution of the homogeneous part, without this one, plus the particular solution. So the blue part is the solution of the homogeneous equation, and the second is a particular solution. And we checked whether this is actually the solution of a homogeneous equation. We did it earlier, partly as a review and partly as a digression. As a matter of fact, partly it was done for preview, as a matter of fact, because we are going to just use it here. So okay, we got all this derivation done, so from this point on, I'm not going to go back and reinvent the wheel. I'm going to use this as a formula, and we're going to start from here. And looks like that's something I'll have to do in a separate video, I guess. Alright, here we go.